Hey everybody, welcome to the Spatial Analyzer technical webinar series for November of 2020. Thanks for joining us. If you're joining us for the first time, these webinars we've been doing for about actually every month this year so far. Welcome to the Spatial Analyzer. And so this has been our goal to increase our functionality and our offerings to our customers through our website and through our YouTube. If you're a guy that grew up in the generation that I grew up in, you know, YouTube is generally kind of the first place that you look when you want to go somewhere for help or information. And so at the beginning of this year, we started doing a monthly webinar series. All of those are available for review on our YouTube channel. Just go to YouTube and select, search for Spatial Analyzer, and you'll find all of those. So we've covered topics like reporting, relationship fitting, point clouds. The last one that we did was a sort of a what's new in our software. And so our goal is to make you guys as handy as you can possibly be in Spatial Analyzer by offering these webinars on a monthly basis. If you have any suggestions for what you would like us to cover for a monthly webinar, we're definitely open to those. So you can post them right now in the chat, or you can send us an email at caleb@kinematics.com. That's my personal email address. And we'd be happy to cover anything that you guys want us to cover in a webinar. We're also available for online direct one-to-one help sessions. So if you go to our website, under the support tab there, you can see an option for booking an hour with an AE. And we've really made tremendous use of that over the recent slowdown and quarantine period that we've been in. And that's been really helpful for customers that either have additional time on their hands or are really kind of needing help one-on-one when we can't travel. And what you do is you go on there and you set up an appointment, and that appointment will schedule an online meeting for you, and then we'll meet virtually, and then we can discuss any topic that you would like related to Spatial Analyzer, and we can help you out in many different ways there. So I really want to encourage you to make use of those resources. It's a fantastic opportunity to get somebody who's been using SA for a long time, myself or one of our other AEs or one of our regional managers, and get a firsthand look at how we would tackle a problem that you're dealing with. So, and that's also helpful for us, as if we can see the custom application that you're working on, then we can really give you the best possible advice for how to tackle that. So stay tuned, subscribe to our YouTube channel, and like I said, if you got any questions, comment and add those down below, and I'll be monitoring those throughout the webinar today. So thanks again, everybody, for joining us, and let's jump right into it. So today what we're talking about is USMN. And USMN stands for Unified Spatial Metrology Network. And so USMN is a way of aligning and characterizing a set of control points or monuments in Spatial Analyzer that is supremely accurate. And so we highly suggest it for any large volume or multi-station applications that you're going to be encountering. So I'm going to go ahead and switch over to our software here, and I'm going to show you one thing before we jump into USMN. Really like to encourage everybody to always be downloading the latest version of the software. One of the ways that you can tell which version of the software you're running is if you look right down here at the bottom of the screen, you'll see the release version. And for right now, I'm running a release that came out just last month in October of 2020. This one is in our final testing stages, and it's going to be ready to be released here very soon. A couple of things that I want to point out to you that you may not know is if you haven't updated SA in a long while, then the ribbons menu may be new to you. We've talked about the ribbons menu in almost all of our previous webinars, so I don't want to take up too much time describing that. I know a lot of people have updated to this current view, but it's really easy to switch back and forth to ribbons. You just select the gear icon. If you're in the classic menu, it looks like a gear, and then you're going to check show ribbon bar. And then once you restart SA, you'll be able to see the ribbon menu. It's really kind of the new way that we're interacting with the software, and it's a fantastic and really efficient way to get to all the commands that you want. One of the first things that people asked for when they started using the ribbon menu is the ability to customize their own tab. And in this latest release that's available in our beta program on our website, kinematics.com, we've actually added that ability. So now, in addition to the standard tabs that are always available in there, you can add your own custom tab with whatever commands arranged in whatever priority and whatever sections you would like them to be arranged. So for the benefit of this demo, I just went in there and I added two of my favorite commands, the best fit points to points command and the relationship groups to objects command. So you can also split things just like in our other tabs, how each one has different areas or sections. You can split things into sections. So if you're wanting to make a custom tab, you may think of this as like your process flow, where you start with step 1 and you have a couple of buttons in there, and then step 2, step 3, step 4, or maybe you want to think of it as a feature specific, where you have one area for your alignments, one area for your analysis, and maybe one area for your reporting. However you want to do that, it's really easy to set up your own custom tab. So I'm just going to show you guys that really quick, and then we can jump right into USMN. If I click on the menu button over here, you'll see that the option down here towards the bottom is options. And this is where you would customize your ribbon. So right now I've added that custom tab. If I want to add an additional tab, I can just select the new tab button, and we'll call this the webinar tab. And I'll hit OK here. And then it's going to ask you for a group. So if you want to create sections in your tab, then you'll just give it a group name. So we'll just call this starting section, and then I'll hit OK here. So now we've got webinar tab and we've got starting, and then all we have to do in order to add a button to that section is click on the starting and select new button. Now I know that I'm going to be talking about USMN, so I'm just going to grab a button that's already available in the ribbon command system. So I'm just going to hit assign command, and I'm going to look for USMN, and we'll hit search here. And then we see that USMN is under the alignments tab, under network alignments and USMN, and then there's a couple of options below that. So I'm just going to hit the standard Unified Spatial Metrology Network button and then hit OK. So we're going to talk about USMN, and then I'm going to hit OK there, and now we've got that button in the webinar tab under the starting section. Just to kind of show you what this would look like, I'm going to add another button in here just so you can kind of get an idea for what it looks like. I'm going to hit assign command, and let's go to a report. So let's say I want to add, a report button to my bar. So now I've got under the reporting tab, I've got new report, report bar, dynamic report. Let's go ahead and just go to the generate quick report button, and I'll hit OK there. And then I'll hit OK. I also want to point out that you do have the option to customize your icons, and you want to lay them out. You can either generate your own custom icons, or you can use the default bitmap, which are included in the ribbon menu automatically. So I'll hit OK there, and now I've got another 2 buttons. I'm just going to hit apply, save those changes, and hit exit. And now when we return to SpatialAnalyzer, you can see we've got our webinar tab, the custom tab that I'd set up before, and then all the regular tabs that are there. So I really want to encourage you guys to check this out, make tabs that are maybe specific to your application or to your setting, and let us know how you like it. If there's something else that we can incorporate into the customized ribbon menu, we'd be really happy to do that. We're still kind of in the learning and growing phase of this, so we'd be really happy to incorporate your feedback whenever we do, and we come out with new releases 3 to 4, sometimes up to 6 times a year. So if you do have any suggestions, please let us know, and we'd be happy to start working to incorporate those into the software. So I'm going to go ahead and go to the webinar tab, and I'm going to talk about USMN. Now, before I do that, I want to talk a little bit about what is uncertainty and why do we need to characterize uncertainty. Well, uncertainty is the part of a measurement which has to be characterized in order to understand how accurate that measurement can actually be. If I go out to a part and I measure that with a yardstick, then I can be fairly confident that I'm measuring that part within maybe plus or minus 1/8 of an inch, maybe a 1/16 of an inch if I'm splitting my divisions up into half. But my uncertainty is about plus or minus a 1/16 of an inch. If I go out with a scale, then that scale can be as accurate as maybe 10 thousandths, or maybe it might even have markings for a thousandths on there as well. But if I measure with just a hand scale, then I can be a little bit more sure about the uncertainty of that measurement as well. And so uncertainty is just a way to characterize that once you've delivered a measurement, how confident are you that that measurement falls in the range that you've specified? And all measurement types are subject to this type of uncertainty. And what I want to show you is how uncertainty changes over distance from the measuring instrument. So as a way to explain that, I'm just going to go ahead and add an instrument into my job file. And I'm going to start it on the 0 point. So now we've got a total station here. And then I'm going to add another instrument. I'm going to add a laser tracker here. So I've got two different instruments, and these instruments have different uncertainty values. And so in order to characterize those, what I'm going to do is I'm going to take some instrument measurements at different distances. So I'm going to go into the construction tab of the ribbon menu, and I'm going to build points manually. I'm just going to build some individual points manually here. So for this one, the first one I'm going to call it is for the total station, and I'm going to call this point 1, and I'm going to build a point at 100, 1,000, and 10,000. So these points are varying distances away from the tracker, and they're going to have varying levels of uncertainty related to that instrument. I'm going to do the same thing for my tracker, so I'm going to go ahead and build some points manually there. This will be for the laser tracker, and we'll just start again with point 1, and we'll build this at 100, 1,000, and 10,000. Now, one of the things you may not know about SpatialAnalyzer is in addition to its ability to perform metrology type of analysis, it can also perform this uncertainty analysis all on its own. And so one of the ways that we do that is using the characteristics of the type of instrument specified. So for these particular instruments, they have three different areas of uncertainty. Both of these have two angular encoders, so an encoder in the azimuth direction, and then an encoder in the elevation direction. And then they also have a very accurate distance meter. So those are all three different ways that combine to form the total uncertainty of the instrument. And the uncertainty values of these two instruments are different. So in this case, the total station has a much more accurate angular encoder than it does have distance measurement. And the laser tracker has a slightly more accurate distance measurement than it does angular encoders. So in order to visualize that, I'm going to go to my Instruments tab. I'm going to go to Instruments Shots, and I'm going to fabricate some shots with uncertainties from each of these instruments. So I'm going to select the total station, and I'm going to select the points that I want to create measurements for. And I'm going to inject random error using uncertainty parameters. So the default parameters that are set up in this total station. So you can see that we've got three measurements now for the total station. We're just going to do the exact same thing with the laser tracker. So we're going to fabricate measurements using the laser tracker and using the points to measure. Okay, so now we have some measured points from both of these instruments at three different distances, and now we just need to generate the uncertainty fields that are related to those measurements from these instruments. So in order to generate those uncertainty fields, and this is a great sort of analysis tool that's available to you in SpatialAnalyzer, we're going to go to the Alignment tab, and under the USMN, under the Network Alignments tab, we're going to choose Coordinate Uncertainty, and we're going to create Point Uncertainty Fields. So I'm going to select that command. I'm going to hit F2. I'm going to generate my uncertainty fields from my total station and hit enter using 1,000 sensitivity samples. And I'm going to do the same thing for my points from my laser tracker. Okay, now what you have to know is that this uncertainty cloud, I'm assuming that you guys can see it based on the resolution of my screen, but what you have to know here is that the size of this uncertainty cloud is actually multiplied by 2,000, and you can change those settings in your user options under the Analysis tab. So my cloud magnification here is 2,000 times. So the actual size of this cloud is 2,000 times larger than the actual uncertainty field. But what I want to point out is not the size of the uncertainty field, but the shape of the uncertainty field. And this really brings into view the differences, the strengths of each of these instruments has. So like I mentioned at the beginning, the total station has a very, very low uncertainty in the angular direction. So as you get further and further away from this tracker, total station, the angular uncertainty does not widen up all that much, but the distance uncertainty is fairly large. So this distance uncertainty spreads out over a large range here. The tracker at this particular distance has a pretty uniform uncertainty cloud, which means the contribution from to the uncertainty from both its angular encoders and its distance measurement are pretty similar here at this range of about 100 inches. Now, if we go to the next measurement, you're going to see that cloud that the total station shot, the purple cloud here, is getting to be a little bit wider in its distribution. So we call that the cigar shape. That cigar shape means that it's a lot longer than it is around. But one thing you'll also notice about the tracker uncertainty cloud is that the further away we get here, it gets actually a little bit flatter. So you can see that from this direction, it looks almost spherical as a cloud. But as we start to get further and further away from the tracker, that uncertainty cloud gets a little bit flatter. And we call that the pancake type cloud. So the pancake cloud has a greater uncertainty in the azimuth and elevation direction as it does in the distance measurement. And then finally, when we get all the way out here to 10,000 inches, you can see the size of this uncertainty cloud gets a lot larger. And also these shapes kind of start to meld together a little bit more. So the uncertainty in the distance and the uncertainty in the angular is a little bit closer, but you can see that there's still sort of a cigar shape to the purple cloud and sort of a pancake shape to the pink cloud. Now, what does that mean? Does that mean that your points are going to be that inaccurate when you get out to that distance? No, of course it's not going to be that inaccurate. But what it means is that your uncertainty is growing the further away you get from a tracker. So why is this important to our study of USMN? Well, in USMN, the goal is to give you the absolute best alignment based on the data that you know. So when we take a look at our points here, if we have two observations on this point, which is the point that we trust more in this situation? Well, obviously the laser tracker at this distance is going to be a much more lower uncertainty or a much more trustworthy point that we can be certain that it's in the location that it says it is than the total station at this. But what we can also do is we can use the strengths of both of these measurements, or if this were even two laser trackers at 90 degrees to each other, we could actually create the intersection of that cloud, and we could increase our confidence that the point lies somewhere in the intersection of both of these clouds. That's really the strength of USMN. It tells you not only where the point is in where both instruments measured it, but what is the most likely location based on the uncertainties of all the observations that you have on it. So I only show this with two different instruments just to illustrate the difference in uncertainty cloud shapes. But the different tracker, if you think of it as a pancake, if we were to measure the point from this location and then we were to go 90 degrees and measure it from this location, then we could reduce our uncertainty on that point by having a tracker either at 90 degrees to it or having another tracker station closer to the location of that point. So moving on, how do we use this in USMN? SpatialAnalyzer has this great information about the uncertainty of each point as it's taken. Well, let's go ahead and open up a help tab here, or a sample file from our help tab. I'm going to go to the sample files, and every copy of SpatialAnalyzer is going to have these sample files that are built right into it. So if you're following along at home, you can open this file with me, or if you want to check it out later, you can do that as well. I'm going to open up this USMN sample file. I'm not going to save my point cloud. So SpatialAnalyzer has USMN that provides us three very important benefits. And the first one of those benefits is just simply an alignment. So this is a measurement situation where we've taken shots on all of these control points. And I'm going to turn on point labels just by pressing Alt L on the keyboard. So Alt L is to turn point labels on and off. And so I'm going to turn on the point labels, and you can see from these that we've measured each of these 13 control points. We've measured them with 4 different measurement instruments, 4 different instruments. So we've got a laser tracker, and a laser radar. So we got 4 different measurement instruments, and we've measured all of these control points. Now, most of the time, what people do when they set up in a new station is they'll shoot those control points and they'll perform their alignment using a best fit. And best fit is a fantastic and really fast way of performing an alignment. But one of the strengths of USMN, which is available in SA Ultimate, is that the USMN, uh-oh, did I lose you guys? Sorry, okay, I think we're still good. All right, so the benefit of USMN and SpatialAnalyzer is that we can actually perform that alignment using Unified Spatial Metrology Network. So I'm going to start with having this, this tracker is going to be our stationary tracker, and we're going to move all of the other 3 trackers to this location. So the way that we perform a USMN is simply to, in the alignment tab, select USMN, and we're going to select Unified Spatial Metrology Network, or alternatively, the keyboard shortcut is Alt-U. I'm going to hit F2, and I'm going to select all of the instruments that I have available in this job file. So I hit OK there, and then I hit Enter. And you can see that each one of these instruments has measured a set of control points. So those control points each have 11 measurements in it. I guess we go from 1 to 13, and then we skip. Each station skips a few. So we have all 13 points, but not every one was measured at every station. So generally, when you're going to set up an inspection, you don't just have control points, right? But you also tie into your control, and then you're going to be measuring some points on your part. So you'll have some other parts, part measurements that'll be listed in here. But we're just going to use the control measurements, which are noted by the point groups here, station 2, 4, 3, and 1. We're going to be using those point groups to perform the USMN. So I hit OK there, and then we get the USMN dialog. So let me point out a few things here. The first one is that the USMN lists all of the instruments that are available in this job file that you're using for your USMN. Now, if you tied into a known or nominal location with one of those stations, then you'll want to uncheck that so that that remains stationary and all of the other stations move to that particular tracker location. So that's what we have here is we have the nominals of these points 1 through 13, and API tracker 3 was aligned to those. The rest of them we just set up and shot. We did not perform any type of alignment. So now we have the API tracker 3, and we want to move all the other 3 instruments to it. So over here in this section, we have a table that shows us each one of those points. So this is the point name, points 5 through 12. Right now it's showing the maximum observed error on that point, which is obviously not anywhere close to where we are because we're 800 inches off here. So before we do anything, I'm just going to go ahead and go to best fit. So if I hit best fit here, this performs the exact same type of alignment that's listed in our best fit. It takes all of the 4 instrument stations or 3 instrument stations, and it best fits those points together. So when we best fit those points together, we come up with a ranking of the error. So for point 5 here, the error based on the alignment of point 5 to the network is, we can see that we have an observation here that uses 144% of our standard deviation range. So anytime you see something that's over 100%, you want to question whether that point is a good observation, or maybe we should choose to leave that observation out of our characterization of this system. So at this point, we have 144% on this one shot. So that was the API shot on point 5. So I'm going to close that out. Let's take a look at which point that is. That's going to be the API shot on this point right here. So maybe somebody didn't put that point down well in that nest. Maybe we had some vibration. Maybe somebody walked past in the middle of the shot or something. But whatever the reason, that point right there is a point that we do not trust as much as the rest of the points. So now with just our best fit, so now we're best fit to it. Let's see what happens when we go to a solve. So a best fit again is averaging all the points together. Now when we go to solve, we see that based on the USMN alignment, that 0.5 actually shows up a lot better because we have a very close observation on 0.5 from the API tracker. So its understanding of 0.5 is a lot higher than the understanding of the shot on 5 from any of the other locations. So we did a solve there. The next thing that happens is when we solve using USMN instead of best fit, our point ranking changes. So now instead of 0.5 being our worst observation, 0.13 is our worst observation, and we see a max error of about 7 thou. And when we calculate all the error of all the observations, that ends up being about 104% of our standard deviation. Now, another thing that's helpful in this table is you can see which instrument station shot each one of these points. So 0.13 was shot by instrument 0, 1, 2, and 3, as were all the other points in this analysis. So we know that 0 is the API, 1 is the Leica, 2 is the laser radar, and 3 is the Faro tracker. So all of these observations happened on 0.13 and all of the points. But if we want to throw out one observation of 0.13, we have 4 observations on it. So maybe we don't need all 4 of those observations if one of those observations is giving us a little bit more error than all the rest of them. So let's take a look at who shot that 104% shot. So if we take a look here, we'll see them ranked. And the shot that is least trustworthy on 0.13 is the API tracker shot here. Now that doesn't mean, that, again, that the tracker itself is faulty. What it means is that the observation has more deviation from that USMN composite point than any of the other observations. So that just means that maybe we don't need to trust that observation and we can rely on the other 3 observations of 0.13. So I'm going to hit OK here, and then I'm going to do something that is helpful because what we want to do is we want to trim outliers. So any observation, in this case there's only one, but any observation that ranks higher than 104% is going to be thrown out of our analysis. So I'm going to go ahead and hit trim outliers. The standard ranking threshold is 100%, and I'm going to trim it at 100%. It goes in and looks at our analysis. It says observation 0 on instrument 0 on 0.13 is at 104%, so it's going to get trimmed. That's fine. Now I hit OK, and then we're going to go ahead and solve one more time. So now when we throw out that poor observation on 0.13, we can see that we've got a blank spot where instrument 0 should have measured it, and we can see that now its ranking drops to just 35%. Now, as happens when you're looking at any database in statistics, when you remove an outlier, automatically your standard deviation is going to make an adjustment, and you might have one more pop up. So now we have 0.10 that uses 110% of the new standard deviation after removing that observation. So what we can do is we can perform all of this, trim outliers, and resolve just by hitting the auto solve button. So this is solve, trim outliers, and resolve. I just did it manually the first time so I could explain each one to you, but now I'm going to hit auto solve, and what we should see is this 0.10, we should exclude observation from instrument 0 as well. So we're going to hit OK there, and then I'm going to go ahead and hit auto solve. Now that we've auto solved, we've refit and look at 0.10. Now we threw out an observation that we didn't really like, and now we've got all of our observations on all of our points are under 100% of our standard deviation range. So that's a fantastic way to say, like, hey, this is a very good understanding of all of our control points. So in addition to the alignment, we've aligned all of our trackers here. We've also calculated the uncertainty of each one of the points, or we can calculate the uncertainty of each one of the points. And we're going to do that by hitting this begin button here. And what that's going to do is going to give us a really good understanding of the uncertainty value for each one of these composite points. So we have 0.4 here, and we have an uncertainty magnitude of about 0.005 of an inch. So that means because we shot 0.4 from 4 different stations, we can be certain that our uncertainty to a 68.26% confidence interval lies within this 0.5 thou range of the given location. So that means that we have a really robust control network here that we can really trust. So now that I really like this uncertainty analysis, I'm going to also tell it that we want to create a composite group. And I'll explain what a composite group is here in just a second. But at this time, we're finished with this USMN analysis. And if there's if you do want to perform an instrument uncertainty analysis, then you can take a look at that as well. And this will tell you, based on these 4 stations and their observations, what is the calculated instrument uncertainty of each one of the instruments in my job. So I want to caution you to not just go ahead and accept this at face value, that this instrument is better or worse than another instrument. This means that under these current conditions, which for the majority of us, we're never measuring under perfect lab-like conditions. So when we say that the uncertainty of the horizontal angle is 1.6 arc seconds, that means that under these conditions that this data was taken, it's an uncertainty of 1.6 arc seconds. That does not mean that it's what the manufacturer advertises or what you could expect in another measurement environment. But just in this measurement environment, our observations are susceptible to an uncertainty of 1.6 arc seconds for this tracker. And you can see for all of them as they go down what their uncertainties are. Now, this is just a good way to understand how your instrument functions in your work environment. If you really want to characterize that unique instrument's uncertainty values in angle distance, then you need to set up in a lab type environment where you're controlling as many of those factors as you possibly can, including having SMRs set up at each station so that you're not moving, inserting and reinserting, removing and reinserting each SMR as you make changes. So you want to remove sources of uncertainty as much as possible if you're interested in characterizing your instrument uncertainty analysis. So that's a little bit outside of the scope of this presentation. So for now, I just want to show you that that's there. And if you have any questions about it, email us. Email me, caleb@kinematics.com or support@kinematics.com, and we can answer those questions about how to characterize your overall instrument uncertainty. But now that we've performed our alignment, we've created our composite group, and we've done our uncertainty analysis on all of our control points. I'm just going to go ahead and hit apply here. And now you'll see that everything is aligned to our control network, and we also get a little uncertainty cloud that's created based on all the observations of that point. So one of the things I want to point out is the third, so the alignment is helpful, the uncertainty is helpful, and then the third thing that's really valuable for USMN is the USMN composite group. And you can think of the composite group as really the best understanding of where each one of these points is. So even though if we zoom in here really closely to point 1, you can see that we've got 4 observations on point 1, and we've also got a composite group. So that composite point shows up as a constructed point, so it means that it was not measured. But it's important to note that this composite point is not just an average of all 4 of these points. It's actually our best understanding of where point 1 is based on the observations of all of the other trackers in this job file. So in order to point that out, I'm just going to construct an average point just by picking individual points here, and I'm going to construct an average point from these 4 observations. And I want to show you the difference between what an average point is, which is basically the best that you can expect from a best fit, and our composite point, which is really the best understanding of that point. So if we create that average point here, what is the distance between where that average point is, or where you would end up if you were doing a best fit, and let's see, Control D, the measure from average point 1 to point 1. And it tells us that that difference in between the two is about 0.005 of an inch. Now that's actually really relatively small for this point. This point has a pretty tight grouping. If we scoot out to one of these other points that's further away, I expect we might actually get a little bit higher of a distance between our composite and our average point. So let me just do this one more time here. So we've got point 13. Here's where our composite is. I don't even have to make that average point in order to ensure you that this is not an average of these 3. But just for reference, I will create that average point. And remember, point 13 is one of the points that we threw out an observation on because that point was so far from the composite point of all the other 3 observations. So for whatever reason, there was a problem with that point 13. Now let's take a look at the distance between this average point and the best understood point, which is our composite point. And now you really get a feel for how this USMN can give us not just a location, but the best understanding of that location. Because in this case, we have about a 3,000ths difference. And if you're talking in laser tracker in the research world, that is a mile. A 3,000ths difference there between what our average point would have gotten us to and what our USMN composite is for that particular point. So USMN, you just zoom in there a little bit closer and it makes it really obvious. USMN is a fantastic way to perform just a basic alignment. It's going to weight these points that we have the best understanding of, weight them higher than the points that we don't really have as low of an uncertainty value on. It's also going to perform the alignment for you. It's going to generate the uncertainty of that point location based on all of the observations. And then finally, it's going to give you a very good understanding of where that point actually is in the composite point group. So anybody that's setting up a control network that you're going to be tying into, if this is tooling related, so for aerospace, when you need to define where all of those tooling balls physically are located on your tool, this is the most accurate way in the industry to specify those tooling ball locations by taking several, it can be the same instrument, but taking several instrument stations and measuring all of those tooling ball locations, some close and some far away. You're going to have a much more accurate understanding of where those points are compared to just measuring them one time from one location, or even measuring one side of the tool and then leapfrogging around to the other side of the tool. That is all ways that you're going to introduce uncertainty into your measurements. So that's all of the information that I have that I wanted to share with you guys on USMN. I don't see any questions in the chat here today. So, but if you do have questions, please feel free to email us at caleb@kinematics.com or support@kinematics.com. Thank you guys for joining us. We're going to do these every month on the first Friday of the month. And if you do have any topics that you would like us to cover, find us on LinkedIn, find us on our webpage, or send us an email. We would love to cover topics that you guys are working on, and we'd love to make a video that you can reference if it's helpful for you in the future. So thank you everybody for coming out, and I'll stick around for just a little bit longer in the chat if you have any questions. And other than that, we'll see you on the next one. Thanks, guys. Hey, I just saw I guess I wasn't getting the chat that was coming up on the YouTube page, but I see that Ruth asked